Well, hello and welcome again to our journey into algebra and number theory. And we've been looking at congruences and developing this notion of the group of, we're going to call the group of units. And we finished off with this example here of U15. U15 meant all the integers in Z15, that is all the integers from 0 up to 14. And U15 consists of those integers that are relatively prime to 15 itself. And so we saw that was 1, 2, 4, 7, 8, 11, 13 and 14. These have no common factor with 15 except 1. And we saw then that this set here, in fact, what we're going to see, if you write down the multiplication table of this, you discover that this in fact is closed under multiplication. But you see it's not closed under addition, because if I add two of these, 1 plus 2 is 3, which is not in the set. On the other hand, every one of these elements has an inverse because of the theorem that we mentioned before, that the elements of this consists of the numbers in Z15 which have inverses. So we have here a new kind of structure which only has one operation, and that is multiplication. It's closed under multiplication. Everything has got inverses, and we're going to call this new kind of structure a group. So, as I mentioned here, we're going to study the structure of the sets UM and ZM in quite a lot of detail later on. U8, for example, is 1, 3, 5, 7. These are the numbers that are relatively prime to 8. This is closed under multiplication, but not addition. As I mentioned before, if you add two elements here, you jump out of the set. You're no longer in the set U8. And every element's got a multiplicative inverse. And this UM is an example of a new kind of structure called a group. So thus far we've had rings which have two operations, and a ring is closed under addition, subtraction and multiplication. We've had a field which again has two operations, and a field is closed under addition, subtraction, multiplication and division by non-zero number. A group is a new sort of structure with just one operation, which we're going to call dot here. So a group is a non-empty set G with an operation dot or star or multiply, whatever you like, such that if you pick two elements in the group, then their product is in the group. The operation obeys the associative law, so if you multiply A times B first and then multiply by C, you get the same answer as if you multiply B and C first and then multiply by A on this side for all elements in the group. G has an identity element, which generally for us is going to be 1, with the property that if you multiply 1 times anything either side, you get back to where you start from. And finally, if A is in the group, then there is an element we're going to call A inverse also in the group. That's important, so that when you multiply A by its inverse or the inverse by A, you get the identity 1. Now it's an exercise to prove that the identity element 1 and the inverse of any element in the X, that these are unique. An example of this is, for example, other sorts of groups, a set of 2 by 2 matrices with determinant 1 under multiplication. So if you take a 2 by 2 matrices, you multiply them together, you get a 2 by 2 matrix, and if the determinant's 1, then the matrix will have an inverse, and the inverse will be a 2 by 2 matrix. There's an identity. In this case, the 1 in the set will look like the identity matrix, like this. So that will be the incarnation. This is the incarnation of the identity in this particular set. Other examples, the set of isometries of an equilateral triangle under composition, and that means if you take an equilateral triangle and you look at its isometries, that is the operations that preserve the shape of it. That is, you can take an equilateral triangle, you can rotate it through 120 degrees once or twice, or 3 times gets you back to where you start from, or you can flip it around any of the axes. This also turns out to form a group under composition. The groups we're going to be looking at, of course, are these UMs. And so Theorem 4 just says UM is a group under the operation of multiplication. Notice that ZM is a group under addition. The 1, the unit in this case, being the number 0. So under addition, Zm also forms a group, but the incarnation of the identity, the 1, turns out to be, of course, the number 0, and it's easy to give a little proof of that yourself. Because we're working with the integers, we also have AB as BA for every A and B in UM. In a general group, this is not the case, because you know, for example, with matrices, matrices A times B is not necessarily the same as B times A. So a group in which this property holds, that AB equals BA, is called an Abelian group. And for us, in this section, all the groups are going to be Abelian because they're all dealing with integers. And I'm just going to refer to them as groups rather than specifically call them Abelian groups. But you should take care that if you do other courses on group theory, then this won't necessarily be the case. So we can construct the multiplication table then, for example, of 1, 3, 7, 9. And this is worth doing here, so let me just do this on a separate page here. So we can take, we're going to take 1, 3, 7, 9, 1, 3, 7, 9, and here's our multiplication. Well, multiplying by 1, of course, doesn't do anything. That's the identity. Now, we're working here modulo, in the example, we're working modulo 10, so this is U10. So everything's done mod 10. So 3 times 3 is 9, 7 3s are 1 mod 10, 9 3s are 7 mod 10. It's symmetric, so I can copy these down because it's an Abelian group. 7 7s are 9 mod 10, 9 7s are 3 mod 10. Again, it's Abelian, so I can put a 3 there, and 9 9s are 1 mod 10. And as you see, what we get here is a Latin square. Every number appears exactly once in every row and column, and in every row and column there is a 1, and that will tell me the inverse of any element. So the inverse of 7 is 3, inverse of 7 is 3, and 9 and 1 are their own inverses. And so we see that this is closed, when we multiply, this is closed under multiplication because this UM forms a group. Well, I wanted to come back and look at congruence equations, since we've been talking about congruences. And a linear congruence equation is an equation of the form AX plus B is congruent to C mod M. So M is your modulus, that's a positive integer. A, B and C are integers, and X is the unknown that we're trying to find in the equation. So various ways of solving these, just a couple of examples. I'm going to solve 2x is congruent to 10 mod 19. Now this, firstly, we would normally just go straight to the answer, but just to explain what's happening here, I can get rid of the congruent sign, make it an equals, by simply saying that says 2x is 10 plus some multiple of 19. Now, k has to be even. This is even, so if there are solutions, this number here must be even, so k is even. So I can write k as twice something, and then I can divide the equation through by 2, and I get x is 5 plus 19j. Or, that's the same as saying x is congruent to 5 mod 19. In other words, looking back here, all I'm doing is I'm going to divide both sides of this by 2. Now we have to be careful because that doesn't always work. So for example, if I do this modulo 20 and repeat the argument, again I've got 2x is 10 plus 20k. Now in this case everything's even, so I don't need to do anything with the k. I can just divide and I get x is 5 plus 10k, and that means x is congruent to 5 mod 10, but I've got to go back mod 20, so I get x is congruent to 5, or 10 plus 5 is 15 modulo 20. So in this case we have more than one solution. Before we try and sort out exactly what's going on here, so this one we could just divide by 2, we get x is 5 mod 19. This one I could divide by 2, but I had to divide the modulus by 2 as well. In this example I've got 16 is congruent to 10 mod 20. Well, again I write this out in usual form, and the trouble is this number here is divisible by 4, this number here is divisible by 4, but oops, 4 does not divide 10, so this number is not divisible by 4, so this system has no solutions. No solutions. Now if you think about the examples that we've done, we see that firstly congruence equations might have one solution, they might have several solutions, or they might have no solutions. The key to understanding what's going on here is to decide whether or not we've got ax plus b congruent to c, whether a is a unit in Zm. A unit, remember, is one which has an inverse. So here we have it. So if m is a positive integer, then ax plus b, ax congruent to b mod m has, well, it's got a unique solution if a is a unit in Zm. That is, if the GCD of a and m is 1. And that's what we saw up in this example. The GCD of 2 and m was 1, and we saw that had a unique solution. It has no solutions if the GCD of a and m does not divide b. And that's what we saw here. The GCD of 16 and 20 is 4, and 4 was not a factor of 10. Now it's got d solutions, this is nice, if the GCD of a and m is d and d divides b. And that's the middle example here. The GCD of 2 and 20 is 2. 2 goes into 10, so 2 is a factor of 10. And the theorem then says we should have two solutions, and we did. So that's the theorem. So I leave parts 1 and 2, I leave as little exercises to do. It's not very hard to show. Simply model what we did in the examples above. For part 3, if d is a factor of b, then I can write this out. I can write out the equation ax is congruent to b mod m. So that means ax minus some multiple jm is equal to b, and I can divide the whole equation through by this d, and which we can then write this as this is a dashed, this d, it should be d there, sorry, so it's a over, I divide the equation through, let me just write that what I just said again, so ax is congruent to b, so that says ax is equal to b plus m times j, and I can take this on the other side, divide by d, and that will give me this. Now these are all integers because d is a factor of a, d is a factor of m, because of this here, and d is a factor of b. So these now are just integers, so I can write this as a dashed x minus m dashed j is b dashed, and then I can read this modulo m. Now a dashed and m dashed now is has a GCD of 1, and so I can now use this idea here. So to finish off the proof, so since a is a unit now in Zm, so a dashed is a unit in Zm star, so the equation has unique solution x is congruent to x naught mod m dashed, which is x naught plus m dashed t. And then I can just keep adding on m dashed until finally I get d minus 1 times m. Once I get d times m, well, that gets you back to your x naught again, because d times m dashed will give you m. And that gets me my d minus 1 solutions, and there they are. Now, in practice, you can use Euclid's algorithm, especially if the numbers are large, to solve congruence equations in much the same way as we solved linear Diophantine equations earlier. So a couple of examples of this. If you want to solve 17x is congruent to 3 mod 401, we use Euclid's algorithm to get the GCD of these two numbers as 1, and I can write that GCD as an integer linear combination of 17 and 401. Turns out to be this from Euclid's algorithm. Multiply both sides by 3 to get me this. Put on my mod 401 glasses and I get just this. And now I can read off, we have 17 times what gives me 3, 17, so it's 354 as the solution. If the numbers are smaller, then we can just use some common sense. So, for example, if I'm solving 7x congruent to 19 mod 31, I might multiply, say, both sides by 5. GCD of 5 and 31 is 1, so that's okay. Now, because 5 times 5 sevens are 35, which is 4 modulo 31, I can then divide by 2, because 2 has a GCD of 1 with 31. That gives me this. And at this stage I could multiply by 16. 16 2s are 32, which is 1, and I get x to 16 mod 31. Similarly, if I had to solve this one, I would firstly divide everything through by 5, including the modulus, because that's the GCD of these two numbers. So I get 5x is 2 mod 7, and then I'd multiply, say, by 3, because 3 5s are 1 mod 7, so I get x is 6 mod 7, and I know it's going to have 5 solutions, that's the GCD, and they're going to be just 6 plus 7, plus 7, plus 7, plus 7, and there are the 5 solutions. On the other hand, 8x congruent to 7 mod 12, the GCD of these numbers is 4, and 4 doesn't divide 7, so there are no solutions. Well, there's one for you to do. I've given you the answer here. How many solutions does this have? Well, you have to check the GCD of these two and check it divides 156. And in the next section, we'll have a look at Wilson's theorem, and then we're going to move on and have a look a little bit more at this notion of groups and group theory.